So I want to go ahead and go through the cellular transport notes today with you also. So you go to your workspace, you go to the cellular transport um, workspace, open it up here. As you can see, we have the Quizlet cards, we have the video that was at the end of the Pear Deck, we have the Pear Deck with the images, then we have your cellular transport notes. To start out, again, like I talked to you guys on Friday with the Pear Deck, got to have a big understanding of the plasma membrane. The plasma membrane, its functions are it allows particles in and out of the cell. It acts as a barrier. Structurally, when we look at it, it is a what we call a phospholipid bilayer, meaning it has two phospholipid heads and tails facing, the tails facing each other, the heads away from each other, which allows the plasma membrane some flexibility, and it also allows it to sit in water. The tails are what we call the hydrophobic area. They don't like water, so they stick into the inside of the plasma membrane. And what you got is you have the hydrophilic heads on the outside that allow the cells to be in water. Also within the plasma membrane, we have what we call integral proteins, which are proteins that go all the way through. They're permanently connected to the plasma membrane, and they are embedded in the hydrophobic layer of the membrane, but they are what allow they're actually hydrophilic on the inside, so they are what allows water to pass through in and out of the cell through the process of osmosis that we're going to talk about. So the integral proteins are pretty important to us. There, some examples there are some examples would be your channel and your carrier proteins. Right here, I'm just trying to make this a little bit bigger so you can see channel and carrier proteins, and then also pumps. Peripherals are not bonded as strongly to the membrane. Peripheral proteins, they sit either on the outside or the inside of the surface, and are held with a few hydrogen. Our thought process, but they help with functions of like collecting cholesterol, different things like that. That will help with fluidity of the cell. So when we talk about cellular transport, we're really talking about two different types. The first one is passive transport, and it's the movement of biochemicals and other atomic molecular substances across that cell membrane without extra energy needed, and it will go from a high to low concentration. Examples would be diffusion, facilitated diffusion, and osmosis. The first one that we are going to talk about is diffusion. Remember, diffusion is the net movement of particles, whether it be a solid or a gas, from an area of high concentration. So you can see right here on this image, an area of high concentration is going to go with the concentration gradient from high to low and spread out over time. And it's going to hit that dynamic equilibrium where you have it spread out equally or semi-equally throughout. When you're looking at these, you can kind of hit on this link here, and that'll take you to an animation also. When we talk about diffusion, we're really talking about concentrations also, which a concentration is a measurement of an amount of substance in a particular area. There are three major factors that affect it, concentration being the first one there. If for diffusion to occur more quickly, we have to have more particle collisions. So if our concentration's higher, we have more solute per solvent, which is how we measure concentration. Excuse me. What we get is we get more interaction, and it happens faster. Diffusion rate happens faster. The temperature, okay, Diffusion rate increases with temperature because particles are moving faster. We give it more energy, they start moving faster, they start colliding faster, and diffusion happens more quickly. Pressure also increases diffusion rate because particles have less room to move around. Again, so they're going to collide more, they're going to interact more. The big difference between facilitated diffusion and diffusion is the incorporation of channel proteins or carrier proteins, those integral proteins again. They are going to allow larger substances to come in and out of the cell that can't easily pass through the plasma membrane. Again, there's no extra energy needed, and it still goes from a high to low concentration. So it is an example of passive transport still. Osmosis is the specific diffusion of water across a selectively permeable membrane. What we are doing is we're moving water molecules to affect the dynamic equilibrium. Instead of moving the solute, we're actually moving the solvent. So we're looking at the solution and trying to get the two solutions, either the solution on the outside or the solution on the inside of the cell, to become in dynamic equilibrium with each other. So what we have is we have movement of water molecules. Okay, so osmosis is specifically water molecules moving across that plasma membrane. We'll talk about three different types of solutions. Isotonic means the cell has the same concentration as the solution that it's in, meaning that water is going to move in and out equally of the cell. We have hypotonic solutions, where hypo means under. So the solute concentration of the solution that the cell is in is under the cell concentration. So water is going to move into the cell to try to get that to be the dynamic equilibrium. Remember, we're talking about moving from a high to low concentration. So water is what we're moving. So it's going to move the water from the area where it's higher in concentration to where it's lower. So in sense, it's going to move water into the cell. So in a hypotonic solution, cells will swell. The hypertonic solution, hyper meaning above, is the solution has a higher solute concentration or concentration gradient. And what it's going to do is it's going to move water again from the cell, from inside the cell, to try to get the two solutions to be in dynamic equilibrium inside and out. So what we have there is we have the cell actually shrinking. Here's three images of that happening. Again, the solution, excuse me, in a hypertonic solution, the solution has a higher solute concentration gradient. So the water is going to move out of the cell into the solution to try to get it to dynamic equilibrium with the cell. And again, your cell is going to shrink. The isotonic, it's equal both inside and out. So we have an equal exchange, or equal water going out, equal water coming in. And the hypotonic, remember, the solution has a lower concentration gradient. So the water is actually going to move from the solution into the cell, making the cell swell. So those are the three that we talk about when we talk about passive transport. Remember, passive transport goes from an area of high concentration to an area of low concentration, saying that we are going to go with the concentration gradient, and then it requires no extra energy. Then we move into active transport. Active transport is the movement of substances across a plasma membrane against the concentration gradient, and it does require energy. So really, active transport is just the opposite of passive. It will go against the concentration gradient, meaning so it will go from a low to a high, and usually happens with the aid of a protein carrier, or protein, integral protein called a carrier protein. We like to refer to them as pumps. Here's an image of the most common one that we talk about is sodium-potassium pumps. Sodium-potassium pump is used to take sodium out of the cell and bring potassium into the cell. When we use our muscles a lot, we do this a lot of movement of sodium out. That's why when you sweat, again, like I explained to you guys the other day, your sweat is very salty in taste. And we're trying to replace or put some potassium back into our cells. Another form of active transport is when we talk about movement of large particles in and out. Remember, bringing particles in is what we call endocytosis. This process with which the cell surrounds a substance on the outside of the environment, enclosing the substance in a portion of the plasma membrane, creating a vesicle and bringing it into the cell. So endo means in. We have two different that we talked about. There is phagocytosis, which is cell devouring, and it engulfs a solid particle. And then we have pinocytosis, which we like to call cell drinking. It's actually fluid endocytosis, where small fluid is brought in to the cell. As you can see, it's brought in as a vesicle. And remember, these vesicles are taken care of by the Golgi apparatus. So they're sent to the Golgi apparatus, or maybe a lysosome would come by and break down that plasma membrane so that they can actually do what they need. Now, the opposite of endocytosis will be exocytosis. So it is actually the secretion at the plasma membrane site. And what we do is cells use exocytosis to expel waste and also to secrete substances, for instance, like hormones that our cell produces. These vesicles are put together again down here, as you can see, by the Golgi apparatus, and then sent out of the cell. So remember, the big things are when we talk about cellular transport. We have the difference between passive and active transport. Passive, no energy needed, no extra energy needed, and moves from an area of high concentration to low concentration. Active transport requires that extra energy, and it goes from against the concentration gradient from a low to high. So make sure you watch these videos and stay up on your studies this week. If you have any questions, please send me an email about this before the quiz on Friday.